Welcome everyone to this first talk of a second day of a conference. It's a great pleasure for me to introduce Hugo Duminil-Copin from the University of Geneva and the IHES. Hugo is a very accomplished mathematician. He's been awarded many prizes in his young career, ranging from the Rollo-Davidson Prize, the Oberwolfer Prize, Loewe Prize, the Bruching Prize, and more recently, the Fields Medal. This is a not exhaustive list of awards he has received, and it does not make justice to the transformation he has made to mathematics as a whole, and in particular to our field of research, probability theory and mathematical physics. He has solved dozens of conjectures that have been lingering since the 70s, waiting for new ideas to come. He has not only introduced new ideas that have changed the way we perceive them, but also took ideas that were existing since times immemorial and gave them their true power. But all his accomplishments and his mathematical career are definitely not reason to invite him for the 70th anniversary of IMPA, but that's not all. Hugo has a very dear relationship with the Institute. He has worked with many people from here, including me, Rob, and Vladas. He has worked with people because of IMPA, like Franco, Marcelo, who's here, and more. I will let him speak about his relationship with IMPA, because I see he has prepared pictures. I'd like to end talking a bit about Hugo as the person. All the prizes and accomplishments he has achieved have not changed his personality a single bit. I interacted with him recently trying to solve a problem, and he was as excited as he was when he was a PhD student and as humble as he was. I definitely advise everyone to watch the video that the IMU has prepared for the award of the Fields Medal. It shows really how math is done the Hugo way, how he interacts with his collaborators. Usually we think about great mathematicians as sitting in the couch, looking at the ceiling and having a great idea. That couldn't be further from the truth in the case of Hugo. It looks much more like a boxing match, where he receives much more punches from the problem than he managed to land.
Standing on chairs.
Yes, standing on chairs. And thanks to his last punches that he managed to land, we have been developing a lot in this field. With no further ado, please, Hugo, he'll be talking about criticality from the perspective of the Ising model. Please, this is a small souvenir from IMPA.
Thank you. I have my own. Thank you very much. Thank you very much. And every single time you introduce me, I'm a little bit afraid because I'm thinking it's going to be so nice and so on, and then I have to, to live for the legend that you are describing, which to me is a little bit too much. But thank you. Yeah, I mean, for me, I was extremely happy to come here for the 70th anniversary because, as you said, IMPA is very important to me. I think very few people know, but I came here even before starting my PhD. The first time it was to listen to a class of Wendelin Werner, and that's when I met Vladas. And after that, we had like many years of collaboration. Vladas introduced me to so many people and collaborators that are very dear to me. Here you have an example where we were, I think it was 2010 or 11, and we were discussing, and in particular here there is a very young guy, Vincent Tassion, that became my closest collaborator, and we were introduced via Vladas, and it's very sad that Vladas cannot be with us today. I have many fond memories of IMPA, and I hope to make many others in the future. So without further ado, let me go to the talk. So I mean, it's not a talk that is intended to probabilists. So I just ask probabilists not to leave the room because there are many of them. I will feel a little bit alone after that. No, so it's rather an introduction to an aspect of our area of research. And the goal is to try through one example, which is the example of the Ising model, try to give you an idea of how we do things in statistical mechanics. And in particular, there will be a few names that will appear in the talk, some just briefly and some a little bit more in details. So what's the example I want to take? I want to take the example of the Ising model. Oh, well, what happened? So the example of the Ising model, which is a model for ferromagnetism. And before so let me try not to, okay. Yeah. So before I tell you more about what you can do on the Ising model, I thought I would do something that we rarely do, which is to try to motivate to you how you end up with the model, okay? How you cook up the model. So this first part is going to be about this. So usually you start from a motivation that you can borrow from many fields of science. Here in this case, it's in physics. So what you do is the following. You take a magnet and you hit it. And Pierre Curie, in 1895, discovered, or maybe rediscovered, if you want to be accurate from the point of view of, I'm sorry to the person that is doing the video, because it's like, when this guy is going to end up moving? Never. Yeah. So what happens is that when you hit the magnet, at some point, it's going to lose its magnetization. So Pierre Curie noticed that. He noticed that it changes depending, I mean, the temperature at which you lose the magnetization changes depending on the material, but it's always there. If you hit a magnet, at some point, it stops being a magnet. And that's exactly the phenomenon we want to understand mathematically. Yes?
Which material are you using in this?
So it's actually an alloy. I don't a mixture of two. Every single time I think, check it to be able to answer this question. Every single time I check it and then forget about this weird word. So I've never been good with that, but that's why I'm a mathematician and not a chemist. That would be a terrible chemist. So anyway, yeah, I will find it and tell you afterwards. So, okay, so how do you cook up the model? Well, first you want to make sense of the object you are manipulating. So what is your, if you want, mathematical magnet? And what you know from physics is that magnets are made of dipoles. They have small constituents. So we call them dipoles or magnetic moments. Here I will call them spins to follow the standard denomination we use in statistical physics. And so you can really think of them as tiny magnets. So your magnet is made of tiny constituents that act like magnets. And so now what we are going to do is we are going to make simplification, like we are trying to build a mathematical caricature in some sense of reality. So we are going to make a few assumptions. So the first one is that the magnets are on the vertices of a lattice. They are regularly spaced. As mathematicians, we like this, right? Because in particular, it gives you access to many tools, like you have a group acting on the space. So for instance, you can get like discrete Fourier analysis or things like that for free. So we want them to be regularly spaced. The second discretization we are going to make is that actually magnets are either pointing in one direction or the opposite. So let's say north or south, or mathematicians plus 1 minus 1. Okay? So these are two assumptions. You don't have to make these assumptions. Actually, if you want in the question at the end, you can ask me. You have actually very interesting models that come up from doing different assumptions. But here we are going to make these assumptions. Okay, and at the end, what you have is that a magnet is, if you want, a function from the vertices into plus minus 1, which is just saying here it's pointing up, here it's pointing down, 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 etc., etc. Okay? So it's a function from the set of vertices into plus or minus 1. And now what you want to be studying is a magnetization of your magnet, so how strong this magnet is, how much aligned with north it is, and you measure that by looking at the average spin. Right? If you get something very close to 1, that means that somehow all the sigma x are pointing up, and you are very strongly attracted by north in some sense. And if this is roughly 0, means that there are roughly as many up and down spins, so you are basically demagnetized. Okay? So that's the first thing. Second thing you want to do is that you introduce a little bit of randomness. So here you have to think about the fact that we are not in the physics of the infinitely large or the infinitely small. We are in the physics of our scale, and the systems are very complex. There are many, many constituents. You should think that there are many, many dipoles in my magnet. So in order to model that, we are going to use randomness. And in order to build up the randomness, like how you sample a magnet at random, we need to know what the energy is, the natural way of defining the energy of a magnet. So let's try to do that. So what we are going to do again, for each magnet, we are going to think of it, each small dipole, we think of it as a magnet. So what he wants is rather be aligned with its neighbors. Magnets have a tendency to align. So there is going to be an energy cost, which is going to be, if the two guys are aligned, it's going to be -1, and if they are disaligned, it's going to be +1. So higher energy if disalignment. Here I'm focusing, I'm going to look now at the total energy, and I'm focusing on pairs of points that are neighbors. This is yet another assumption. Actually, we know how to do things when it's not what we call the nearest neighbor model, where only neighboring dipoles interact. But for this talk, I think it's quite sufficient to focus on this case. Okay, and once we have the energy, well, we do what Boltzmann tells us to do, which is you take a measure which is going to give a probability which is lower when you have higher energy, and in fact, the only natural form you want to be taking is exponential of minus a parameter times energy. This parameter, we now know very well that it should be interpreted as the temperature. Okay, so the probability of a magnet is proportional to exponential minus 1/t times energy. So if temperature is infinite, 1/t is 0, you are looking at a uniform measure. You just don't care about being aligned with your neighbors. If t tends to 0, 1/t tends to infinity, and then the energy is preponderant, you absolutely want to minimize the energy, meaning there are two configurations that will be the only one that you can reach, which is all up or all down. Okay? And in between, well, you have a competition between the energy and the entropy, the number of configurations with a given energy. Okay? And that's what is going to be interesting. So that's called the Ising model on the box lambda at temperature T. So now, what is the equivalent of the magnetization? Well, now that we sample our model at random, we take the mean magnetization, right? We average the magnetization against our measure. And here, the first thing we see is that, unfortunately, we always get 0. And this is very natural because every magnet and its complete opposite, where you reverse all the spins, have the same probability. So you get exactly 0, whatever, in some sense, the temperature. So that leads me to my third step in the building of the model, which is I want to break this plus-minus symmetry. And this, in some sense, should correspond to the intuition that usually your magnet is somewhere, is in, if it's on Earth, it's in a magnetic field, the magnetic field of the Earth, right? So you want to be breaking the symmetry, and what you can do is simply force the spins on the boundary of your magnet to be aligned with what you think is your external magnetic field. So you align, so you just force them to be plus, for instance. To be honest, for people who know a little bit the Ising model, this is not a natural way of implementing a magnetic field, an external magnetic field, but for the talk, it's much simpler like that. So, and you can match the two ways. By the way, this has absolutely 0 sense, right? The video is just to make the red dot move. It's not, usually people are much more interested. They're like, oh, now there is a red dot. Where is the red dot? Okay, so these are just Glauber dynamics, but it's not going to be discussed in this time. So a way of sampling this. Okay, so when you force the spins on the boundary to be plus, you obtain a different measure. If you want the measure, the previous measure, but condition on the boundary to be plus. So I'm going to call it mu plus. And notice that now, if you look at the mean, at the average of m, there is no reason you get 0 anymore because you cannot reverse all the spins. And in fact, well, you can reverse all the spins inside, but you notice that then on the boundary it changes the energy. And one thing you can do, you have to trust me, is check that in fact you get something strictly positive in this case. So the magnet has a tendency to align with external. Okay, but this is not what we are fully interested in. Because if you take a very small box, it's very easy to see that your magnetization is strictly positive. But as I said, a magnet is made of like a very large number of tiny constituents. So what I'm truly interested in is the very large boxes. Or if you prefer, because we are mathematicians, we have this freedom, we can just take the limit. So take the limit when you take box to ZD. Take bigger and bigger boxes. And this quantity, look at what it does. So it actually decreases when you increase the box, and it's going to decrease to a quantity m star of t that we call the spontaneous magnetization. And that's this quantity that we want to understand. So spontaneous magnetization, that's this quantity that we want to understand whether it's strictly positive or 0. You could think, you have something positive, but the sequence could go to 0 or not, and we want to understand if that happens or not. Okay? So again, you take the infinite volume, which is the last piece of the puzzle to construct your model. Okay? So at this stage, it's a good way to do good time to do a first recap. So first thing, the physical phenomena lead to a mathematical model by making some assumptions, right? We discretize. We use randomness, and we took the infinite limit. And these 3 steps are actually something you do quite often in statistical physics. And just to give you some examples, if you look at interface growth, you can end up with models that then converge to what we call the KPZ equation, or they are in the KPZ universality class. If you look at the kinetic theory of gas, you have models called the R-sphere gases. And then this also, when you take the limits, you can get to descriptions of gas. Or if you look at nuclei of heavy atoms, you can look at the spectral properties of very large random matrices. So you have different models. This is just 3 examples just to tell you the Ising model is not an isolated case. And these kind of steps where you simplify, introduce randomness, go to the limit, are actually this kind of 3 common steps to almost all these phenomena, all these models. And the interest of this model is not only that they model the original problem, is that they are also very rich mathematical models. So you can really get some very rich behavior from them, which makes them interesting. Okay, so we get to the second step. So I motivated to you the introduction of the Ising model. Now what do we do? So we would like to understand that there is a phase transition, exactly like we see in nature. If the temperature is small enough, we have an actual magnet, so the spontaneous magnetization is strictly positive. And when you go above this critical temperature, you end up with 0 magnetization. You don't have a magnet anymore. So this is called the ferromagnetic phase. This is called the paramagnetic phase. And as I already mentioned, so this was not very pedagogical, but this is called the critical temperature. Okay. So do we have a phase transition? That's the goal of this second part of the talk. Okay, so this is a good point to tell you a little bit about the history of the model, because it's an interesting history. At the very beginning, in fact, there were, it was a tough start. We cannot say that the Ising model was immediately recognized as something brilliant. So Ernst Ising, after which the model is named, was a PhD advisor of Lenz, who introduced the model. To be fully honest, we quite often say that Lenz made a few assumptions that I would say would naturally lead to the model, but the first formulation of the Hamiltonian is actually due to Ising. So we should maybe give him the credit. So what he did is that on the line, he proved that Tc, the critical temperature, is 0. What does it mean? It means as soon as you have a positive temperature, zero magnetization. So there is no one-dimensional magnet in this sense. So that led to this following quote from Ernst Ising. I discussed the result of my paper with Professor Lenz and Wolfgang Pauli, and there was some disappointment that it didn't show the expected ferromagnetic properties. So some disappointment is a very like, I think that was a huge disappointment. It's a little bit understated here. Ernst Ising actually even left academia after that. He learned only like 30 years later that his name was one of the most cited names in physics. And so it's true that he was very unlucky because he also predicted that this would happen in any dimension. Keep that in mind for later. So there was, I mean, not only this was terrible because in some sense it looked like a terrible model for ferromagnetism, but there was an even worse thing happening at the time, for Ising, not for the rest of the world. This worst thing was the development of quantum physics. It's one of the golden age of quantum physics. And in particular, Werner Heisenberg, from the Heisenberg uncertainty principle, he introduced a model for ferromagnetism where this time, the small spin that are just taking plus minus value, they were replaced by the spin angular momentum of electrons in atoms. And this is much closer to reality. So in fact, the Ising model has this huge default that it's not even based on the actual development at the time of physics explaining the phenomenon. So these were like two catastrophic news for the model. But there were a few pros. So first, Rudolf Peirce in 1936 did prove that not only Ising was wrong to predict that it's always zero critical temperature on any graph, it's actually zero only when you look at a line. So this is a quite wrong conjecture. But so he proved that TC of ZD is always strictly positive, and in fact, you can even make sense of fractals, and we still expect that it's true as soon as the Hausdorff dimension is larger than 1. So it's really only linear objects have this behavior of having TC equals zero. And Peirce also observed a second thing, which I think is probably even more important, is that he observed that if you try to model, for instance, binary alloys or more generally like cooperative phenomena, you actually use, people introduce independently the same model, always the Ising model. So the Ising model is maybe a not so great like model for ferromagnetism, but it's a fairly good model for many different phenomena. So you have a trade-off, right? You have a model which is not optimal for the original thing, but it actually models very different phenomena, and that's very interesting from the point of view of mathematics, because that means that you may give like common justification to several phenomena. I will come back to this later. So this was, at least, it helped keeping the Ising model alive. And what really, I would say, changed the deal is a result by Lars and Zager in 1942. So a few years later, Lars and Zager did the following. He proved that what we call the free energy, I need to move like that if I want to work. So the free energy, which is, if you want, the typical energy per unit of volume in your magnet, you remember the definition of the energy, you take the typical energy per unit of volume. If you look at Z2, so if you look at the two-dimensional Ising model, it's this formula. It's not, you don't need to look at all the details. The important thing is that it's a closed formula. You have an actual value, a formula for this free energy. And this is something absolutely spectacular. It was, by the way, it's not easy to prove. Whoa, what did I do? I think I didn't move. So it made me pay. OK, let's restart like that. OK, good. So just to mention, so this is a difficult, the original on Zager thing is a difficult result. It was simplified by Brurier-Kaufmann in 1949. And then, actually, many different approaches were found based on combinatorics, algebra, analysis. It's a very good example of a problem that can actually gather many different areas of mathematics in the same direction. So just to mention, I mentioned the free energy. Maybe I should not have, but I wanted you to know about this result. Yeah, that works better. But something maybe more related to what I said up to now is, I mean, my key player was a spontaneous magnetization, M star of T. So let me just mention that Chen-Ning Yang in 1952, actually using similar ideas to what Onsager and Kaufman did, he managed to compute the spontaneous magnetization. And you get this formula, which you see in particular, yeah, that works, gives you that Tc is 2 over log 1 plus square root 2. So you can even compute, not only can you prove by pairs that there is a critical temperature, but you can, in fact, compute it in 2 dimensions. Yang here is a Yang that many people know. Yang Mills, Yang Baxter, Lee Yang. I mean, he's one of the most influential physicists of the 20th century. And this was one of his early achievements. He was very young at the time. That was not a joke. Okay, just a board. Okay, so one thing I want you to remember is that this is on Z2. And just to throw one word that you may have seen or heard already in a lecture, it's all these results, they are based on what we call the integrability of the model. It's some very special property, and in particular, it breaks as soon as you don't work on a planar lattice. But when I say as soon as, it's not that you even need to go to 3 dimensions. If you add, say, an edge from this vertex to this vertex to this vertex, etc., so you go to next to nearest neighbors, already the model completely, the integrability completely breaks. So it's a very versatile property. But if you have it, you can do a lot with it. Okay, that's for the second part of the talk. So now we know there is a phase transition, and we even know that in 2 dimensions you can compute the critical point. So what's the next step? Well, you know, we are scientists, so you keep zooming. So the next level of precision you want to get is to understand what's the type of phase transition. There are 2 types of phase transition in nature. There are the discontinuous one. So a discontinuous phase transition is typically the example of water freezing, right? If you look at the difference in volume per, the volume per unit of water, if you go from 0.1 to minus 0.1, you have a discontinuity. I need to remember that I'm talking to mathematicians, because when you talk to a non-mathematician, you have to explain, you jump, blah, blah. Sorry. So there is a discontinuity by 10%, basically. And if you want to play with it, you can even make bottles explode, and then you regret to have shown that to your kids, usually. But yeah. So this is a discontinuous phase transition. If you look at Curie's temperature, Curie's experiments, this is actually pulled out from the original writing of Curie. You see that when you look at the magnetization, there is no discontinuity. It's it's not differentiable, clearly, you see, but it's continuous. So do you see the same thing for the Ising models? That's the question. And the answer in 2 dimensions, at least, is easy. In 2 dimensions, you take your formula, you let T go to Tc, and you see that it actually goes to 0. It goes like T minus Tc to the 1 over 8. It's some kind of very cool power that you may not guess just like that, but it's continuous. Okay, very good. So, you know, why did I do that? Because, let's remember that, yes, that's good. Let's remember that magnets are 3-dimensional objects to start with. And in fact, the Ising model is natural in any dimension, but clearly dimension 3 seems like the natural model when you want to understand ferromagnetism. And the problem is that if you look at 3 dimensions, we are not in the integrable case anymore, right? So in particular, just to tell you, Tc, the critical temperature, we have no clue what this is. And my guess is that there is no way there is a nice formula for it. Okay? The spontaneous magnetization as a function of the temperature, we have no clue what this is. It's kind of not surprising. If you cannot get the critical temperature, it would be even more surprising to have the whole function, right? So we don't know what these things are precisely, but still you can define the critical temperature implicitly. It's the first time you have a strictly positive spontaneous magnetization. And what we did with Vladas Sidoravicius and Michael Eisenman is that we proved that at the critical temperature, this spontaneous magnetization is 0. And in fact, as soon as you have that, you have to trust me, it's very easy to prove that, in fact, the whole function is continuous. The only bad thing, the only bad thing that could happen is that actually it will be strictly positive at TC. That's the only bad thing. Okay, so this is a theorem. At least you saw one theorem. And I wanted to give you an idea of the proof of this theorem because I think it relies on some very nice feature that was developed in the last 50 years in the case of the Ising model, but even, I mean, more generally, it was developed much more in the last 10 years for many other models. It's the idea of graphical representation. So I want to give you a little bit of just a glimpse at what this is. Okay, so idea of the proof. So first thing I need to do, I need to switch gears and introduce a new player, a new key player. This key player is called the spin-spin correlation. It's simply the average of sigma 0, sigma x, say. So you take two spins and you look how much they have a tendency to align. So you look at the average of the product. If this average is 0, that just means they are kind of independent. If it's strictly positive, they have a tendency to align. And this is a formula, but here I just put this symbol to say that I can consider that for plus or for the measure without plus boundary condition. Okay, so again, you take the limit when you look at larger and larger boxes, and we are interested in the large-scale behavior, so what happens when x goes to infinity? How two dipoles far in my magnet, in terms of graph distance, how do they interact? Okay. First thing you can do, and this is not difficult, is that you can look at the spin-spin correlation and prove that it converges to the magnetization squared. This is not that surprising because if you think about it, if you take two spins and you send one to infinity, you look at the spin further and further away, they should basically start to be independent. But in fact, just the average of one spin for the plus measure, it's like averaging. I mean, I define the magnetization as an average in space, right? But in fact, if you believe you have some translation invariance, ergodicity, all these things, and in fact you do, then it's the same. You can just look at the average of one spin. So one spin average against mu plus gives you the spontaneous magnetization. So then this is a kind of natural thing to expect, that you should converge to the square because you have your two spins. Okay. In fact, you can also, and this I will not really justify, but you can prove that the average of sigma 0, sigma x tends to 0. So that looks very good. It looks like you have, yes, it looks like you have the spontaneous magnetization equals 0. But you notice, I think you all notice that here there is a catch, which is that in one case I look at the plus measure, and in the other case I look at the measure without this plus restriction. So basically the difficulty is that my slide disappeared without me willing to. But the difficulty is that you need to prove that the plus measure and the measure without the plus, which we call the free measure, that they are equal. It's the whole difficulty, in fact. So if I have that equality, then it's easy to conclude. Okay, so let me put this aside for a minute and do a true normal, like just a break, and discuss just a different object. Okay? So this different object is called Percolation Theory. It's a model of random subgraph of a given graph. So you take a graph lambda, and you take a random subgraph omega that here I depicted by the red edges. Okay? Just to give you an example, the simplest model you can imagine is that for every edge, you put it red with probability p and gray with probability 1 minus p. So you keep each edge in your subgraph omega with probability p, independently of the other edges. You just sample independently for edges. This is called Bernoulli percolation. And you are interested in the connectivity properties of this random subgraph, omega. So here is, for instance, two different things. So what happens is that this is at p equals 0.49, something like that. And this is at p equals 0.51. So in this case, it's a little bit below 1/2. You have a little bit less red than gray. And what you see, the colors correspond to the connected components of my graph. So what you see is that they are all small. There is no big connected component in my box. When p is 0.51, so you have slightly more red than gray, what you end up with is a huge connected component. It happens to be red, but it has no connection with that. And only small, like the second largest is actually tiny. Okay? So actually, the mathematical physicists in the room know that this is not p equals 0.49 and p equals 0.51 because this cluster should be as big as those. Otherwise, I'm sorry for that. I'm lying to you. That's what I'm trying to tell you. But it's for your own good. So the important thing here is that, in fact, you see, when you vary p, the behavior of the model changes drastically, and in fact, it changes drastically at 0.5. It's called a critical parameter, like the temperature, but this time it's a critical parameter for the density, if you want. It's a critical parameter of the percolation model, and there is a phase transition between a model where if you think of porosity, if you think that you pump water in some place in your graph, it can go in the connected component corresponding to this place. So here you would have a porous medium, because if you pump water anywhere in the red, it will go basically everywhere in your graph. And here, on contrary, you will have something which is not porous at all, where water, it's hermetic to water. So this is percolation. And by the way, I just want to mention, because I need to say a few things to the probabilists in the room. Many of them, I think I didn't know about that. It's one of my PhD students who digs this information, Mendes Sulamara. He noticed that Rosalind Franklin, the person from, the Rosalind Franklin from DNA, actually during the war was exactly doing what I would call is a perfect percolation experiment. She was taking coal and pumping gas in it with different size of molecules and different temperature for the coal, and see when this gas was percolating or not, was going through or not. So this is like 20 years before the actual introduction of, or 15 years before the actual introduction of the mathematical model, there was this very accurate experimentation on percolation. So yet again, she got forgotten for that. So she seems to be brilliant and unlucky. So yeah, I wanted to mention her here. So what's the connection between percolation theory and the rest of the talk? There is one. Is that, in fact, when you look at the correlation in your magnet, in the Ising model, they can be encoded by probabilities that a certain random graph, a certain percolation model, the probability that the 2 points where your spins are actually connected in the graph. So let me rephrase that. The spin-spin correlation are, I don't know why things appear like that, sorry. The spin-spin, look only at that. The spin-spin correlations are rewritten as a probability for a certain percolation model that 0 is connected to x, that there is a red path between 0 and x. And I should be very clear, this percolation is not Bernoulli percolation. It's not a model where you decide that edges are open, are in omega or not independently, which makes the thing much more difficult to study. But there is a model, so it's called the random current representation. And the advantage is that, of course, the link between the Ising model and the percolation model doesn't stop just at the encoding of the simple 2-point spin-spin correlation. For instance, you can compare the plus spin-spin correlation to the free spin-spin correlation, and the difference is going to be encoded by the probability that 0 and x are connected to infinity. But there you start to feel, okay, that's maybe good, because just before, if I just rewind a little bit and think about the picture, the red picture, what definitely happened is that there was a huge connected component, but only one, right? And if you would look at the infinite actually size, you will see this red is infinite, and this is the only infinite connected component. There is a unique infinite connected component. But if you think, of course you need to prove it, but if you think that this happens also for this percolation model,
that if there is an infinite connected component, it's unique, then you get automatically that 0 and x must be connected if they are both connected to infinity. They are in the same connected component. There is only one. Okay, but 0 connected to x, this is this quantity, right? So what did you just prove? You proved that this is smaller or equal to twice this. But now you can use this goes to 0. That was my claim that I didn't want to explain to you. And this goes to the spontaneous magnetization square. So it's equal to 0. I mean, I'm hiding a few things. I'm lying to you again. I don't lie all the time, but you know, sometimes. Don't extrapolate too much on this, the last 5 minutes. But I wanted to give you an idea of the proof because I think it really shows this interesting link between two models. Remember, the Ising model is rather a model for ferromagnetism or cooperative phenomena. Percolation is really a model of porosity. I mean, at the level of physics, these two phenomena have no connection whatsoever. But when you look at math, when you elevate a little bit yourself, you should not say that. Well, in this crowd, it's fine. So then you see the connection between the two. So that's... So this connection, by the way, I mean, this type of connection go far back. Okay, I don't want to be taking credit for the connection itself. What happens is that these models that you obtain when you do graphical representation of spin systems, they are never Bernoulli percolation. They are always models where your random graph is sampled in a very difficult way with a lot of dependencies. So what did I do, if you want me to tell you a little bit about me for once, because up to now it was not so much connected to me, is that you need to understand the percolation models when they have dependencies. And this actually is a difficult task. So you need to develop a theory of dependent percolation, basically. And once you do it, you can, for instance, prove that there is a unique infinite connected component and prove, in fact, many other things. Okay. Very good. I have until 50, right? Okay, so let me try to advance. No. The pictures, it's the most important thing, right? Now that's embarrassing. Well, okay, you see, it's called panic. Okay, at least you have the pictures, and they disappeared again. Yeah, okay. And I didn't learn, but maybe it's in both directions. That's fine. So anyway, these are pictures of different percolation models. I wanted to show them because there is a very large diversity of models of connectivity. Here, for instance, you have what we call Boolean percolation, where you sample random balls. Here you have a dependent percolation model, which is actually connected to many different models. It's called Fortuny-Castle percolation. And here, just for, I wanted to mention that here it's a random height model that is obtained by taking eigenfunctions, or random linear combination of eigenfunctions of Laplacian on the sphere. It's called the monochromatic random wave. Does it mean I should stop? No. And it's a very nice model. It has different behavior than these models on certain aspects and very similar on others. So you have a large variety of possible models. Okay, let me try to rush through the last part, where maybe I'm going to go a little bit faster. It's maybe more for the probabilists, I don't know. But I hope I will keep everybody on board still. So what do you do once you know it's continuous phase transition? Well, you keep zooming. You want to understand even more on the model. And one thing that happens when you have continuous phase transition, it's called a critical phenomena in physics, is that you have what we call emergent laws. So laws that were not present when you look at your model if you don't look at it precisely. But if you tune the parameters of the model precisely, then you end up with new properties. And I thought I would give you one example, which is the four-dimensional Ising model at criticality. Yes, that works well. Okay, so what happens for the four-dimensional Ising model at criticality is that if you look at correlations, not of two spins, but two n spins, 4, 6, 8, then in fact, if you want to understand those parameters, you can just, in fact, it's sufficient to understand the two-point correlation because there is what we call an approximate Wick rule. If you look at the Gaussian process, and you look at the correlations between two endpoints in the Gaussian process, it's exactly equal to the sum of the pairings of the product of correlations between 2 points. That's the Wick rule. It's a characterization of Gaussian processes, and Gaussian processes are one of the simplest processes you can imagine in probability. So here what it says is that if you look at the critical parameter and you let the distance between the point go to infinity, then approximately you end up with a Gaussian process. So this here means equivalent. It tends to 1 when the distance between the points goes to infinity. And so again, this is a kind of approximate Wick law. It's actually an exact one in the limit. And it's something quite important for the following reason. So in dimension 4 and more, in dimension, 5 and more, Eisenman and independently Fröhlich in 1982 proved this result with a speed here of decay to 1, of convergence to 1, which is polynomial, like L to some power. In dimension 4, we prove this result with a log speed of convergence. And the reason is that this is, in some sense, dimension 4 is a critical dimension where this happens in the most subtle way, in some sense. And it's, as usual, when it's difficult, it's usually the place where you exactly want to look. The four-dimensional Ising model is actually related to constructive field theory. So if you want to construct a quantum field theory, there is a beautiful theorem that allows you to rephrase this question of defining the quantum field theory into a question of defining a random distribution, what we call a Euclidean field theory. And this is particularly interesting in 4 dimension because, on the quantum side, 4 dimension is actually the dimension of our space, at least for quantum physics. I will not go to higher things. But so in some sense, you are led naturally to try to understand what type of random function, random distribution you can construct in 4D. And there was a natural guess that if you take a Hamiltonian, which we call a 5-4 lattice model, you could maybe construct a quantum field theory describing the interaction of 2 particles. The problem is that the 5-4 lattice models are close cousin to the Ising model. In some sense, the Ising model is the strongest, like the hardest 5-4 model. And for the 5-4 model, for the Ising model, we proved this, in fact, rephrased exactly as the limit, the random distribution you obtain in the limit is actually a generalized Gaussian process. So that means that on the quantum side, you get what we call a trivial field theory, meaning a field theory, a quantum field theory that describes non-interacting particles. So this is a no-go theorem, if you want, that this thing is saying you cannot take the 5-4 model and end up with a non-trivial quantum field theory. You will have to do something more complicated. And you see, for instance, it's not a baby step towards Young Mills. It's already just this we don't understand how to do. It's just how do you get 2 particles to interact from the quantum field theory. This is not the answer. So what is a no-go theorem from the point of view of the constructive quantum field theorist in me? Is actually a very good theorem. It's a positive theorem from the statistical mechanics person, right? Because it tells you that if you want to understand 2 endpoint correlation, you only need to understand 2-point correlation. And the end of the talk, which I will not be describing, is that in fact this 2-point correlation, they actually exhibit another emergent law, which is that they are invariant by rotation, scaling, and translation. And it's not the case at the discrete level. So you have an emergent Gaussianity, and you have an emergent, you have emergent symmetries. And once you describe all of this, you end up, for the probabilist in the room, you end up with Gaussian free field. This is the only possible scaling limit in 4 dimensions. So I wanted just to give you this small glimpse at what we actually do today, right? These other things are maybe what we did a few years or 10 or decades before. Nowadays, what do we do in statistical physics? We usually aim at understanding what are these emergent laws and how can we prove they exist. Well, thank you very much for your attention, and thank you for hosting me in IMPA yet again.
So are there questions or comments?
I scared all of you? Ah, okay. No. Percy is never scared.
Hugo, you know your community knows such wonderful things about the Ising model, and I've asked you this over the years, but you're leading a project to try to write it down so that the rest of us can understand, to have a book about the Ising model. What's the progress on your 3 volumes, 6 volumes? Could you talk about, if somebody wants to understand what you guys know about the Ising model, where can we look?
Yeah, so I made a huge project, a huge progress in this project of writing finally a book on Ising, which is that we are now more to write it. I increased I thought my amount of time is not increasing. Yes, it went from 1 to 3 5 years ago, and now it's 7. So be careful, it's increasing fast. And if you show any interest, you will be in the, no. So I think now it's more concrete. But it's a huge task. I mean, there are so much to write, and you want to be doing it right the first time. So, yeah, and yeah, our life don't get less busy, right, with time. So yeah, but that's an important thing indeed.
So about this Gaussianity in dimension 4,
Yeah.
if you take maybe other models like Potts model or ON model or something like that, do you expect something different from Gaussianity at a critical point?
So the Potts model, for instance, they don't have a continuous phase transition in dimension 3 and more. So already you lose even the step before. So it's a mean field behavior, but just the mean field behavior is a discontinuous phase transition there. So you need a model for which the mean field behavior is continuous. So for spin ON, it's fine. You would have, and I think you expect triviality. We don't know how to do it even for the XY model, which would be the next step. It seems difficult because we use very delicate properties of the graphical representation that I mentioned, which for now, we don't exactly know how to extend it to XY. And this is actually one of the big, I think, directions of research to understand now everything we understand for Ising, to try to understand it for these other models, this generalization.
Thank you.
More questions? So last time we met, you talked about some out of this world developments in the physics community about the conformal analysis of critical models in higher dimensions.
Yeah.
Have you heard back from them again?
I mean, he's now my neighbor in IHES, right? I mean, one of the key players. So, I mean, so indeed there is this beautiful development in physics, which is trying. So I mentioned this emergent symmetry, this rotation, scale, and translation invariance. In fact, you have a stronger emergent symmetry, which is called conformal invariance. You expect invariance under any conformal map. So in 2 dimensions, it gives you a lot because you have many conformal maps in 2 dimensions. And in particular, once you have conformal invariance, you can classify very easily all the, I mean, not very easily, sorry. You can classify all the possible behavior. Of course, you need to prove conformal invariance, but that's another problem. But in 3D, these people showed, so Slava Ryzhkov and company, they showed that even though you have way fewer conformal maps in 3 dimensions, you can still extract some information from them. And in particular, so they don't know how to compute critical exponents or things like that, but if you take the Ising model, they managed to prove that certain exponents are really like in a tiny area of possible values, which is actually better than, you know, Monte Carlo analysis of the Ising model or things like that. Like the level of precision is below. Of course, I mean, you have to believe one of the two, but it's below and it's in the level, in the bubble of possible values from the Monte Carlo. So it's very, very exciting area of research. And I think it's an area of research that mathematicians should actually focus on more, because we are naturally led to think, okay, there is
basically zero chance of proving conformal invariance in 3D, which is maybe true, but who knows, in the future. But here, I think it's a very interesting area where you can just assume you have conformal invariance and try to see what you can get with it. Because in particular, does it characterize really the critical exponents? For now, they know it's kind of, they are reducing every day, in some sense, the size of the area of the possible values. Is there only like one value for each critical exponent, for instance? These, I think, are very interesting questions, and I don't think many mathematicians tried to look deep in what they do, and they would like people to look at this. I know from Slava that they would love that. Yeah.
Okay, if there are no more comments or questions. Oh, just a second, please.
I must say, I was a bit surprised that you did not mention normalization and universality.
Renormalization? Good. So it's time that played against me. Okay, let me just show you the next slide, because there is universality in the next slide. Well, whatever, you have to believe me, but there is universality in the next slide. So indeed, in order, on the physics side, to predict, for instance, the emergent symmetries, you would rely heavily on the renormalization group. And there are ways of turning this in a rigorous fashion for the Ising model in certain cases. And this is a very interesting area of research. It's just, I had to stop at some point. And you are more than I am. So you decide when I stop and not the opposite. But yes, yeah, renormalization plays a key role in all of this.
Okay, so I think it's a good time to thank Hugo again.
Thank you.